Dr. Shekhar Munde, Professor Ravi, distinguished colleagues. It's really a privilege for me to be here with you on 58th Foundation Day of IITM. It's also a privileged day for me to talk to you about what India is doing in the planetary exploration programs. And I would like to take an example and run you through to how we do this kind of missions, and to tell you what we have done in the last 1 decade or so, and what our plan is in the future. I would like to dedicate this talk to the founder of PRL, Professor Vikram Sarabhai, whose birth centenary we are celebrating this year. And during the lunch, Professor Munde was asking me about this young Indian entrepreneurs and scientists who built up the country. And PRL was established in 1947, the year of our independence. And he was born in 1919. So he was 28 years old when he founded PRL. So you can imagine the caliber and the entrepreneurship he had when he founded PRL. And he is also called the father of Indian space program, that he not only established PRL, but he actually founded the Indian space program by building it right from the scratch. So I would like to dedicate it to Vikram Sarabhai. So what I'm going to talk to you about the planetary exploration program, and I would like to talk more on science and challenges, and what kind of challenges we really face when we do this kind of programs. As you see here in the bottom, there are rockets, which are basically the launch vehicles, which we use to send the satellite into space. And India now has the capability of developing its own rockets and flying it from its own soil. So this is the PSLV, or Polar Satellite Launch Vehicles, and this is the GSLV XL, or GSLV Mark III, I should say, which is being used for sending the satellites into space. This has been used for sending Chandrayaan-1 and the Mangalyaan, and this has been used for sending the Chandrayaan-2 into space. In the bottom, you also see some of this Chandrayaan-1 or Mangalyaan over here. And I will run you through the mission Mangalyaan and take you to a journey to Mars and how we actually achieved this rare feat of going to Mars. Before going to that, let me just tell you about the planetary, the solar system. So what you're seeing over here is our solar system, which we now call as the new solar system, essentially because Pluto, which used to be the 9th planet in our solar system, now comes in the category of dwarf planet or minor planets. And there are planets beyond Pluto, like Makemake, Hyume, Eris, and there are reasons behind that why we call them as minor planets or dwarf planets. I'm not going to detail of that. But if you look at this, you will say that there are two classes of planets in our solar system. The one which we call as inner planets, which are much smaller in size. And then you have outer planets, or giant planets, or big planets, which are in the outer part of solar system, which consists of Jupiter, Saturn, Uranus, and Neptune. And we call these as gas giants, and this we call icy giants. And these are called terrestrial or rocky planets because they have surfaces, whereas when you go into outer part of solar system, they don't have real surfaces. You also have small bodies like asteroids and comets, which are also very essential aspects or essential elements of the solar system, and we need to know fully all these elements. We really want to know better the planet Earth itself. If you look at these 4 inner planets, you will say Earth and Venus are both same size, Mars is roughly half, Mercury is about 1/3 of the Earth. But when you compare them with the other 4 giant planets, you will say Earth is about 1/10 of the size of the biggest planet in the solar system, which is Jupiter. And if you compare this with Sun, and here you will say where the Earth is, there is a small dot over here with respect to Sun. And on the planet Earth, you can say where India is and where Pune is and then IITM, and then this hall. So you can imagine how small we are with respect to size of the biggest star of our solar system, and now you can think about the stars and the galaxies and stuff like that. So dimensions are really huge. Now I will take you to journey to Mars using Indian MOM, which stands for Mars Orbiter Mission. MOM is the word which most of the kids now use for mother. Mom kya kar rahi ho, kya ho raha hai. And so Indian MOM is around Mars. We had this mission in 2013. We reached Mars in 2014. 5 years hence, we are still in orbit around Mars. So I am going to give you a journey how we reach Mars. I just mentioned about these two, but this is the deep space network which we use when we want to communicate when we are in space, and we use it using radio waves. Now comparing just a little bit more about Earth and Mars before we go into Mars mission. If you compare these two quantities, that is the length of the day on Mars and Earth, they are both similar, about 24 hours, as well as the tilt which you see over here, both on Earth and Mars is similar. That means Mars also has season like Earth, the 4 seasons which Earth has. But since Mars is beyond the Earth's orbit, it's about 1.5 AU, 1 AU is the mean distance between Sun and Earth, and receives lesser amount of sunlight, which you have to account for when you are talking about mission. And being smaller in size, it has much smaller gravity, which in turn has implications for the atmosphere itself. But when you talk about the composition of the atmosphere also, you will see the Earth is nitrogen and oxygen dominated. It's about, you can say, 80% nitrogen, 20% oxygen, forgetting about many traces gases. But if you look at Mars, you say it is carbon dioxide dominated. So CO2 is a dominant gas on Mars. So as I just mentioned, we had the launch of the Mars Orbiter mission on 5th of November 2013, and we reached Mars on September 24, 2014 after 10 months of journey. And we are in orbit still, though we had the planned lifetime of 6 months. So though we planned for the mission for 6 months, we are surviving more than 5 years, and still it's going strong. When we took up this kind of mission, we had two challenges, or two objectives I should say. The first one is of course the technological objectives, because we were going to have this kind of mission for the first time. And that's why we call it as interplanetary mission, because we had the Chandrayaan-1 mission before that, but now we are breaking the gravity of the Earth and going beyond that. When we went to Chandrayaan-1 mission to Moon, we were still under the influence of gravity of the Earth, because Moon is going around the Earth. So the technological objectives were designing and realizing a Mars orbiter mission with the capability to survive, perform earthbound maneuvers, cruise phase of about 10 months, getting captured and then working around Mars. There are a lot of challenges which comes with the deep space communication, navigation and management, and of course autonomy features which was actually required to handle this kind of deep space communications and navigation issues. And I will talk about that later. And then we had the science objectives, which was basically exploration of the Mars surface, morphology, mineralogy, atmospheric composition using 5 indigenous experiments. So when we had this mission, we had the launch on 5th of November, and we were going around the Earth, gaining velocities, and then we departed from Earth to have a travel to the Mars, and we have to reach this place. When Mars was here, when we departed from Earth, it also has to come at the right time, at the right place. So these kind of precise calculations has to be done a priori when we talk about this kind of missions. Talking about the satellite itself, it's about 1300 kgs, and a large amount of it is actually fuel or propellant, which we have to carry, because we have to perform a lot of maneuvers in space. This is the solar panel which you see over here, which is required to generate power for all the functioning of the spacecraft, and you can see here the huge antenna which is required for the communication. So this, as you go away from the sun, you require more and more larger solar panels, because you have to generate what you call power using solar cells, and the sunlight is falling as 1 by r square as you go moving away. So, you need bigger sizes. Now, first of the challenges which came when we are talking about this kind of mission is that two of the major events, that is the fourth stage separation of the spacecraft and the separation and the fourth stage ignition, both of these were happening in the southern Pacific Ocean, and there is no land there. So, what we have to do is we have to actually send ship from India called Yamuna and Nalanda, and they were actually stationed in South Pacific to capture these two events. And this is the first time we had done this kind of exercise, because we never required to have this. They captured the signal, providing very important clues about at what time, location, attitude and latitude and longitude we have the separation of the spacecraft. And that is precisely required because you have to do all the orbit maneuvers based on this separation of the spacecraft from the launch vehicle. So, this is the first challenge which we undertook when we are talking about a mission to Mars. This is the kind of deep space network which we have close to Bangalore in Bailalu, which is required to communicate with the spacecraft when we are in orbit around Mars. This is a 32-meter dish, and you can imagine the size of this with respect to 3 humans which are standing over here. Now, talking about the other challenges which we take, and this is how the what you call the antenna on the spacecraft looks like. This is a 2.2 meter antenna, which also is one of the biggest antenna which we have ever used for any missions of India. The second what you call challenge came from spacecraft autonomy. When we talk about a mission around Earth like our INSAT series or IRS or even going to moon, we can communicate and get back what is happening on the spacecraft within a second. But when we are talking about going to Mars, the round trip time travel can be as large as 40 minutes. So, that means if something happens on the spacecraft, you will say hello, everything is fine, and you have to wait for 40 minutes telling yes, everything is fine. So, if something happens on the spacecraft, you will not know or what to do. That means you have to have autonomy on the spacecraft to take its own decisions, and that was realized again for the first time using fault detection, isolation and reconfiguration. That is called FTR logic, which was uses the AOCES and the BDHR systems or TMTC packages. And this has been actually used at many crucial phases of the mission, and it has been performing very well. As we move away from the sun, we receive much lesser sunlight. So, the amount of light is reduced and you have to have larger solar panels, but also because the light is reduced, you go to a lower temperatures, and therefore, you have to qualify various subsystems to very cold temperatures. And that is again a challenge which came up for this kind of missions, because we have to have everything qualified for a very, very low temperatures to function in space. Now, this is how the spacecraft looks like. So, I will now just run through how the spacecraft is built up and what we all do for developing this kind of things. So, this is the bare body of the spacecraft which you see. It is about a 1.5 meter cuboid in a clean room in Bangalore. We start populating this with various subsystems which you see over here. This is the main spacecraft, and this is the tanks. The bottom the inside which you see over here is actually the fuel tank. You start populating it with all the stuffs on board, and then you put all the sensors and things like that. You see here these are all sensors of the spacecraft. The thrusters are down here, and then you actually cover it with a multi-layer insulation, because this works as a blanket. So, as in the cold weather we take blanket when we sleep in the night, or we use jackets to cover up for keeping warm, this multi-layer insulation is actually required on the spacecraft to separate it from direct heating as well as heat loss from the spacecraft to the outside. And after all this, we actually prepare it for a thermo vacuum test. That means, now we have to see that the whole spacecraft will work in space and work with perfection. So, now we have to test all the subsystems of the spacecraft working independently and together to make sure that things are fine. So you see here the whole spacecraft is now getting loaded into a big chamber, which you see over here. This is 11-meter chamber, and this whole spacecraft will go down in the pedestal and sits, and then this lid which you see over here will get closed down, and we create vacuum and then load it with the heating to see the functionality in the vacuum conditions. The reason being that when you are in space, it is vacuum, but you are getting heated up or getting cold from one side or the other side, and you have to see that the subsystem of the spacecraft has to function very well. We also test all the solar panels and also put this whole spacecraft in a chamber which we call an anechoic chamber, because you have to also see that the radio frequencies at which we communicate with the spacecraft does not get interfered with anything which a subsystem of the spacecraft is producing. So it means the frequency at which spacecraft communicate to the ground or the ground communicate to the spacecraft should not get interfered by anything else on the spacecraft. Subsequent to that, we put this in a huge truck and then move this whole spacecraft to Sriharikota, that is a launch pad or the launch port of India. So this is Bangalore over here, this Sriharikota, and this spacecraft travels from Bangalore to Sriharikota. This is the map of India, and you can see here various centers of ISRO where various systems and subsystems of the rocketry or the spacecraft or the sensors are getting developed. In Sriharikota, when the spacecraft arrives, we keep it in a clean room, which you see over here, and then we do post-transportation test. That means it has not traveled almost like 350 kilometers, so we have to see that everything is safe on the spacecraft, and after that we fuel the spacecraft. So now, right now, the fueling of the spacecraft is going on, and subsequent to that we put it on the top of the launch vehicle. So this is the adapter of the fourth stage of the launch vehicle. These are all computers of the launch vehicle, and this is the adapter on which the MOM spacecraft is sitting. And after that, we will be covering this with a heat shield. You see here two big shields, so it will just engulf that and it will look like this. So now you see here, this is the heat shields covering the spacecraft, and the spacecraft is inside this, and it is almost ready for the launch. So you can see here the whole launch vehicle, the 4-stage PSLVs. This is the first stage, the second stage, third stage, and fourth stage. This is a 44-meter tall launch vehicle, and this is all vertically assembled in this MST which you see over here behind. So it's a vertical assembly of the launch vehicle at the Sriharikota. You can see it much better over here, and after this assembly, this whole building starts moving back. It goes almost like away about a kilometer when the launch takes place. So you can see here the vertical assembly of the building. So these are various sub-stages of the first stage getting assembled here along with the strap-ons on the sides. This is the second stage getting assembled here, and then you have the fourth stage with the adapter over which the spacecraft will come and sit. So this is how the launch is almost ready, and this whole mobile tower which you see over here start pulling back on these big wheels which you see over here and the rails, and this goes back when the launch actually takes place. At the back, you are also seeing another launch pad. This is the second launch pad of India, and then we have now the third launch pad also coming up, as well as the third assembly building also coming up, because now the requirement for launching has increased and we need to have more launch pads as well as assembly buildings. So we had the launch on 5th of November 2013 in the middle of the day, and this is how the ignition started. And I will show you a small movie, if it works here, which will show you about the launch of the MOM. So this is the launch of the MOM mission. This is about 1.5 minutes to 2 minutes only for the first stage. The rocket has fired and it's going up. The first stage is in action along with the strap-ons. You cannot hear the commentary well because I think it's not picking up, but still you can see the rocket very well. This is the first stage of the rocket being utilized. and very soon you will see the strap-on separation here. So, whatever is the burnt stages of the strap-ons, we push them off. Yeah, just now there was a small hinge, you must have seen it here, which is basically strap-ons got separated. So, this is the how the launch took place. This is only the first stage of the whole journey, and after this we went into an orbit of close to 23,000 by 200 kilometers, and subsequent to that, whenever the spacecraft used to come close to the Earth, we used to fire it to make it more and more elliptical. And the reason for that is we have to escape Earth. To escape Earth means we have to have the velocity as more than the escape velocity, which is 11.2 kilometer per second. So, we were all doing this exercise continuing for almost like 25 days, and we used to have the firing in the middle of the night mostly or early morning. And during this period, we also tested some of the sensors and the subsystem of the spacecraft, so that we know everything is working fine. So, this is one of the pictures which was taken by the Mars color camera on the spacecraft, where we took the image of the photograph of the Earth focusing on India, and this is from almost like 70,000 kilometer away. Finally, on 1st of December, we had the longest burn, which was almost like 22 minutes, and that made this orbit change from this elliptical orbit to Earth escaping orbit, and we started moving away from the Mother Earth. Now, talking about the spacecraft itself, this is how the stowed spacecraft looks like, and this is in the exploded views. You can see here how it various subsystems of the spacecraft looks like over here, and it has been flown by keeping it in the heat shield of the launch vehicle. So, the experiments on this MOM spacecraft, there are 5 of them: the Mars color camera, the methane sensor for Mars, and thermal infrared spectrometer. They were all developed in the Space Application Center in Ahmedabad. The Laboratory for Electro-Optic Sensors in Bangalore developed the Lyman alpha photometer, and the MENCA, the Mars Exospheric Neutral Combustion Analyzer, was developed at Vikram Sarabhai Space Center at Space Physics Laboratory, Trivandrum, where I was the PI at that time. So, they are all accommodated on the spacecraft at different locations. You see over here, these are 3 imaging sensors along with the lab, almost looking at the one side, whereas the MENCA is mounted like this, and it faces along the roll axis, that is the velocity vector of the spacecraft, because it has to in situ detect the various atmospheric composition of species present in the Martian atmosphere. So, this is how whole the control room looks like in mission control in Bangalore. We keep a constant watch as we are moving away from Earth to Mars. And during this, we also do all the calculations of when we are leaving, at what angle we are leaving, and then going to heliocentric orbit and reaching to the place where the Mars would arrive. We did these calculations and found that we have to do 4 mid-course corrections, which is listed over here. We did first one on 11th of December 2013. The second one was expected in April of 2014, but we did it in June. The third one was expected in August 2014, which was not required because we had such a fantastic separation and then leaving the Earth, that no correction was required. And then the fourth one, which was expected in September 14th of 2014, but we did it in September 22nd, that is 2 days prior to actually Mars orbit insertion. And there is a story behind that, and the story is about the propulsion challenge. This is the first time which we face this kind of issue, because after 10 months we have to now reignite this engine which was used. And it is almost like put your car for 10 months out of use, and now you want to start the car and say car will work or not. So, what has to be done? We have to actually test it on the ground. So, we take the similar engine, we put it in the ground in the simulated conditions of the environment of the space, and we test it for 6 months. We found it is working. We tested after 1 year, we found it is working, but then this is not the same engine which is flying. So, we thought that why don't we use the same engine for doing the maneuver correction, and that will also give us a confidence, and as well as it will test that the functioning of the engine is working. So, what we did all the calculation, found that if we fire this engine for 3.88 seconds, which will give the required maneuver which we need, and will give all the data which will test about the functionality and the performance. And we did this 2 days prior to the D-Day on September 22nd. It functioned very well. It did the whatever we are required to do the maneuver, and also gave us the data which says that the engine is going to perform very well. And that is how we became very confident that we will have the success on 24th of September. So, when we do this kind of missions for ground support, not only we use our Bangalore deep space, but also deep space from all over the world, and these are all Goldstone, Madrid and Canberra, supported by JPL in US. So, they are all sending the best wishes. You see here from Madrid, from Goldstone, from Canberra and from JPL, they were all sending good luck, best wishes messages. This is how we got inserted. This is very interesting story. Now, this is Mars, this is the direction to the sun, this is the direction towards the earth. So, we are approaching the Mars on the night side or back side. Okay. So, as soon as you come in this side, you get communication blackout. So, there is no communication with the earth, and since we are approaching from the night side or back side, and you do not have power generation. So, you are on the batteries. So, what you have to do? You have to put on the autonomy features, you have to load all the what we call commands and controls, and let it do what it is supposed to do. It is called blind operations. Okay. So, what we did? We had this approach, we rotated the spacecraft, has to fire in the same direction in which we are moving. Why? Because now we have to slow down the velocity to get captured in the gravity of the Mars. We started firing the engine. You see here, this is the engine firing, the orange part, and before that itself we were in the shadow. So, we are already on the batteries, the black portion which you see here in the shadow, and almost like 3 minutes of firing, this violet color, we have communication blackout. So, we do not know. So, we only knew engine has fired, everything is working fine, but after that no signal. We are all sitting for almost like 20 minutes in the mission control that time. All our heartbeats were beating, we are all waiting for the first signal to come, and we come to know what has happened. Signal got resumed, and we came to know that yes, mom has entered the Mars orbit. And the news came at 8 a.m. on that day that mom has successfully entered the Martian orbit, and that made India the first country in the world to have a successful insertion of a Mars orbiter mission around Mars in the first attempt. And that was really a rare feat, and PM Modi, who was actually there in the mission control, congratulating the Indian chief, Dr. Radhakrishnan, that time. But then we thought, what is the proof that we have reached? So, we rotated the whole spacecraft to take a picture, and this is the first picture which we got, which shows yes, we are around Mars, and that was actually presented, and I was also celebrating that, the first picture. So, this was the success story of Indian Mars orbiter mission, but not only that, soon this story spread, and one of my friend from US in the same evening sent me this photograph. He says, mom has become so famous, it has come on the Coke diet. And then we have Google celebrating 1 month later on October 24th the success of the Indian Mars orbiter mission. Amul had its own story. It says, ISRO's cow, Amul, ye cheez badi hai mast, Mars. And then National Geographic actually took the photographs which was taken by the Mars orbiter mission and put it in its cover page. And not only that, the government of India also understood this rare technological feat which India has achieved, and that is why it has put the Mangalyaan on the back side of 2005. So, this is the kind of images which we are getting now, full disk images for last 5 years, almost like two full solar, what I should say, 2 Martian years, because 1 Martian is about 2 Earth year. So, almost like 2.5, And now we know that how the cycles are changing. This is the north and this is south. This is in the time of aphelion for Mars. The condensation happens on both north and south poles. You can see here features like this, which shows these are high altitude clouds putting up the shadows on the surface, or even pictures like this, which is very rare for the satellite of Mars, Phobos, passing in front of Mars, or even high altitude clouds, which you see over here. I don't know whether you can see it here, the small white kind of streak here, which is completely detached from the surface, and the altitude is expected to be about 100 kilometers. So how one can have high altitude clouds at an altitude of about 100 kilometers, so completely detached on the Mars, which is not a phenomenon seen on the Earth. So there are many features which has come out, or even the canyon, the biggest canyon in the solar system, which you see over here, and you see these features which are basically clouds showing up the shadows, or you can see even the clear Grand Canyon, which is the same Valles of Marineris, and it changes as the season changes on the case of Mars. Or you can even see the big mountains and the leeward side of the mountains producing clouds. So there are many features which have been now getting understood by this mission, and there is a lot of science which is coming out, including the science from the Menka instrument where I had worked, and where we actually provided the first observation of the exosphere of Mars in the evening time, where we showed that CO2 dominated atmosphere actually changes to an O dominated atmosphere, you see here on the top, and where you see that oxygen actually dominates when you go in the higher atmosphere at somewhere around 250 to 300 kilometer compared to CO2, which is the dominant constituent of the Martian atmosphere. And also we discovered suprathermal argon in the exosphere of Mars, and that is precisely because we have seen two kind of what you call density profiles in the case of argon, and one of them has a scale height much higher, which in turn means it has a larger temperatures, almost like 100 Kelvin higher. And what its implications are that if you have hotter species in the exosphere of Mars, it will easily escape. So that means the escape process in the upper atmosphere or exosphere of Mars will be much more rapid than what we have been thinking so far. So there are a lot of implications of the science which has come out from this kind of mission. Now I will switch gear and talk a little bit about the moon and what we have been doing so far and what we plan to do. And I like this image very much because this shows the Earth as seen from moon. So this is the surface of the moon in the bottom, which you see over here, and this is the Earth, and this is a picture taken on 22nd of July 2009 using Chandrayaan-1 mission. And this is the image which we had taken because we wanted to see the shadow of the moon falling on the Earth, because this was a solar eclipse day. So we rotated the whole spacecraft to look back at the Earth. But if you want to look at the Earth, because this is, this is a time of monsoon, and India is somewhere here, but you cannot see it. I hope you can see it better here, and now you can see India. And this is again a picture taken by the Chandrayaan-1, that is from the moon, or you can see it's still better here, right? And we are somewhere here in Pune. So this mission, the Chandrayaan-1, was also a very important mission for India. This is the first moon mission in the year 2008. We had the launch on 22nd of October. We reached the moon on 8th of November, and we had 11 experiments on board, which are all listed over here, and 3 of them were actually being flown for the first time in planetary exploration. It was truly international in character because we have 10 countries participating in it. You can see here much better all this various payloads or the experiments loaded on the spacecraft, and the SARA experiment is the one where I was directly involved as a PI, which had 2 sensors, SEEN and SIM. Chandrayaan-1 had made very important contributions in the lunar science, and the first and foremost is of course the discovery of water. Till that time we were not knowing that water is present there. We were all thinking moon is bone dry, but Chandrayaan-1 mission told that no, water is present on the moon, and it is present in ample amount, and it is a huge distribution with much more amount of water present in the polar regions compared to the low latitudes. It has also discovered not only water in the surface, but in the permanently shadowed areas, in the craters, as well as in the exosphere. It has actually proven the lunar magma hypothesis by the presence of large amount of crystal feldspars. It has discovered mini magnetosphere on the moon and also the reflection of solar wind protons and also volcanic activities as recent as 100 million years. Earlier we were all thinking there is no volcanic activity happening on the moon, it is geologically dead, but this mission has told no, it could be even as early as 10 million years. There are more recent data which is coming being analyzed from the Chandrayaan-1 which is telling that this number can come down to 10 million years. And then of course, many of these features on the surfaces and the rallies which have been found out. And many of this has actually produced the cover pages of the journals like Science or Geophysical Letter. This talks about discovery of water on the moon. It shows more water in the polar regions compared to low latitude, but it is there globally. And this talks about the discovery of mini magnetosphere, which is produced by very small localized magnetic field or magnetic anomalies on the lunar surface with the size of the magnetosphere as low as 300 kilometers. Whereas on the Earth, because of the presence of a large magnetic field or intrinsic magnetic field on the Earth, we have a huge magnetosphere which is 10 times bigger than the size of the Earth itself. This is a movie of how the surface of the moon looks like. Let me see if this one plays over here. It was, oh great, it is working. So, this is how the surface of the moon looks like. You can see here it is a lot of undulations on the surface. All these features which you are seeing here are actually craters of varying dimensions from centimeters to meters to kilometers to tens to thousands of kilometers. And the big craters we call as the basins. So, the moon is full of craters, crater के अंदर crater के बाहर crater, इधर crater, उधर crater, everywhere crater ही crater है. You see here all these are craters actually. So, anything which is falling on the surface of the moon because it does not have an atmosphere like Earth creates a crater, and it is preserved because there is no weathering. So, you will find craters inside craters, craters outside craters, and all possible ways of craters. I will just highlight one point which I was trying to say about discovery of mini magnetosphere, and this is how we are all understanding the interaction of the solar wind, which is actually a wind of plasma coming from the sun interacting with the moon. And we were all thinking that this comes and interacts, there is nothing much happening, it all get absorbed on the day side, there is a huge cavity getting formed in the night side which we call a plasma wake. But this picture has totally changed to this, where we now see that a lot of processes happening on the day side, but not only on the day side, there is a lot of plasma reaching on the night side, which was not at all known so far, and that has made this plasma environment around the moon to be so active, and now a lot of work is going on. Almost like 100 papers have come out after Chandrayaan-1 mission talking about the plasma environment of the moon, how the plasma is actually getting transported from day side to night side, what happens to solar wind when it comes and interacts, and how you can see plasma not only reaching night side, but hitting the night side, which has come out from the evidences from the Chandrayaan-1 mission. So, I will not talk about much detail of this. Coming to the Chandrayaan-2 mission, you must have all heard about it, whole country is aware about it. This is the most complicated mission which India has undertaken, because it not only had the orbiter like what we had in the Chandrayaan-1 mission or the Mangalyaan, but it also had a lander, and inside the lander is the rover. So, it was not only that orbiter mission, but it was actually a lander mission. A lander had to land on the lunar surface, and then the rover was supposed to come out. This is how the two modules looks like. This is the orbiter module, this is the lander module, and this is the orbiter module in the clean room, and we are all assembling this. So, I will not run through the Chandrayaan-1 because its features are very similar to any mission which we assemble in the clean rooms. And this is the rover which is actually sitting inside the lander which you see over here, and all tests being done inside the clean rooms about the movement of the rover coming out and then moving onto the lunar bed. We had done a lot of simulations of how the rover will actually move out onto the lunar surface. This is the composite module. So, we had the launch of the Chandrayaan-2 on 22nd of July, which many of you must have watched. It was in the middle of the day, and after the launch we went into this orbit of going around the Earth, which is again similar to what we had done in the previous missions. And you might be wondering why we do this. This is because this is the most optimum way of utilizing the fuel. If you want to go straight away from Earth to Moon, you may have to spend large amount of fuel, or you should have a much more powerful rocket. Same thing we can do by increasing the velocity slowly and then going into an orbit where you escape Earth and starts moving towards the Moon. So, we actually had the launch on 22nd. We went to an orbit like this. We started going away from the Earth on 14th of August and then actually got inserted into an orbit around the Moon on 20th of August. And after that, we started making this orbit 100 kilometers circular. So, you can see here that there were also few orbits around the Moon before we were going into 100 kilometers circular polar orbit, which is the actual orbit desired. And after that, we separated the spacecraft from the lander, and the lander went into this 100 by 30 kilometer orbit, whereas the spacecraft was going into 100 kilometers. So, now there were two spacecraft around the Moon, which we are handling together, and this is again for the first time. These are some of the pictures which has come out after we got inserted into an orbit around the Moon. And on the orbiter, we had 8 experiments, and these experiments are meant to provide us much more detailed information compared to what has come from the Chandrayaan-1 mission. We had for the first time flying a IIRS, which is infrared spectrometer, working from 0.8 to 5 micron, and that is a band where one can actually do a full mapping of OH and H2O molecules, not only in the polar regions, but also across the whole globe of the Moon. We had CLASS, which is going to give us information about the elemental composition, OHRC, which is having the highest resolution on the lunar surface. We have dual frequency synthetic aperture radar. This is again for the first time, L and X band SAR being flying, because that is going to provide us information about beneath the surface to a few meters, and that will also tell us about the ice deposits in the polar regions. We have a CHASE experiment, which is going to provide us information about the lunar exosphere, and dual frequency radio science experiment, which is called LAMBA, which will provide us information about the electron density distribution. And then we have XSM, which is basically an instrument to look at the solar X-rays, which is impacting the lunar surface and providing what you call information for elemental composition, and the TMC, which provides us information about the what you call morphology and topography of the lunar surface. And on the lander, we had 4 experiments, and on the rover we had 2. These 2 were actually meant to go at different places and to sample the soil to provide us elemental composition by 2 different techniques: LIPS, which stands for laser induced breakdown spectroscopy, and APXS, which stands for alpha particle access spectrometer. And on the lander, we had 4 experiments. We have a what you call seismometer. We have an experiment to get the information of the temperature beneath the surface to a 10 centimeter depth using chaste, and then we have a Langmuir probe experiment very close to the lunar surface, providing the electron density distribution. So, the current status, you must be already knowing about what happened on 7th of September early morning. Right now, all the experiments on the orbiters are performing very well. They have been commissioned and started giving signs. So, you can say that performance of all the orbiter payloads is satisfactory, and they are started doing now their scheduled or configured science experiment science schedules. This is how the images have started coming out from OHRC, which has a resolution of as high as 25 centimeters. This is the strip of 25 meters. So, you can see here small minor features of the lunar surface can be very clearly seen for the first time. This is the highest possible resolution images we have got. So far, no other mission has provided this. Let's skip this. Also, we came to know about what happens when the moon goes across the geotail of the earth. As moon goes around the earth for almost like 1/3 of its time, it is going through the earth bow shock and geotail, and the what you call the interaction of the moon with the solar wind changes, because now it is saved by the earth's magnetosphere. So, what happens during that time? There is a lot of good science which is going to come out, we see a lot of features like this which has come out from the class instrument. This is actually meant for looking X-ray emissions or reflected solar X-rays from the lunar surface elements. But you are seeing signatures of very what you call large counts, seeing when it is passing through the tail. And these looks to be pixie, which is coming out from the high energy electrons which is there in the plasma tail of the earth, coming to detector and making this kind of signals. That in turn means that we can actually qualify this high energy charged particles which is present in the Earth's magnetotail. You also seen this minor flares you see here. This is the GOES instrument data which is from the NASA, and this is our XSM solar X-ray monitor developed in PRL flying on the Chandrayaan-1. It has a much better capability compared to what is provided to the international community at a cadence of almost like 1 second. So, every 1 second we have a spectrum of the solar X-rays or the solar X-ray spectrum in 1 to 15 kV band, and this is going to be a boon for not only for the Chandrayaan-1 mission, but for the solar science community, because they are going to get information at almost like 2 order of magnitude better than what is available so far. We have seen many examples of terrain mapping camera operating. This is one of them which is being shown over here, where we can see features very close to almost like where is this one here? Here 4 kilometers. So, you can see here the rallies seen over here, and these kind of features actually are used for tagging the lat long of on the lunar surface, and then using this you can actually georeference the whole image. There is a lot of information coming out from this kind of terrain mapping camera. You can see one of the craters over here, and it is so illuminated that this side is sun illuminated, this is dark, and if you look at these ones, you will see that they are all similar to this, but they look like inverted. So, this is actually some kind of what you call image illusion which gets created, but actually this side, this is actually a crater, this side is sun illuminated and this side is dark. And we are now able to see this crater, and crater counting is one of the way to actually understand how old a particular region on the surface of the moon is, or you can see images like this. We also got very good information about the surface and the craters using the L and S band SAR, and you can see here very clearly a crater, and inside that you can see small craters, and if the sunlight is not reaching at these places, you will not be able to see them. But using the centrifugal radar, we are able to probe this, and now we can get much more information about not only the depth of these craters, but also what is beneath the surface. And this is another example of that. You can see even probing the crater floors is almost like half a meter to several meters deep inside the craters. What next? So, we are working on a mission to sun called Aditya L1. Aditya means sun. So, this is a mission to study the sun from L1 point, and I will tell about that. This mission is actually meant to understand the sun's photosphere, chromosphere and outer layer of the sun, that is the corona, using multi-wavelength observations. So, we will have a coronagraph which will work in the visible, we will have UV imager, soft and hard X-rays, as well as particle experiments and a magnetometer to probe the solar wind, which is a plasma coming out from the sun, as well as the electromagnetic radiation, that is the photons in the visible, UV and soft and hard X-rays. This mission is going to go next year, and this is the point which you called as L1 point, and this is the point between sun and earth on a line joining it, and as the earth goes around, this point also goes around the earth. This is a Lagrangian point. It is more or less like a point which you can say the orbit is quite stable, and the advantage with that is one can continuously see the sun uninterrupted 24/7, whereas if you are going around the earth, at some point of time you will be at the back side of the earth as seen from the sun. But this L1 point give you a very important vantage point that you can make continuous observation of the sun, and that is why we have chosen this to put this Aditya L1 at L1 point, and using those 7 experiments on board, we are actually going to probe the sun and understand much more intricacies as well as 4 times the distance between sun and moon. So, it's, and if you put the solar wind velocity of about 350 to 400 km per second, it will take about an hour or so for the solar wind to reach Earth. So, that means you get information a priori to what is coming towards the Earth from that one point, and that is why it is going to be useful for space weathering point of view to understand what are the processes which will get initiated when coronal mass ejections or CMEs comes and hits the planet Earth. So, these are the details of various experiments which is going to fly on that, and I will not go into detail of that. And the next is the future missions. We are working on a mission to Mars as well as to Venus. Mars, I have just told you the story, but this is going to be much more complex mission compared to the MOM-1, because now we are going to make it as a fully science driven in terms of flying many experiments to understand the processes on the surface of the Mars, how its surface and atmosphere interaction takes place, and how the lower atmosphere to middle atmosphere to upper atmosphere interaction, how the dust clouds are getting formed. There is a lot of science which is coming out from previous missions about the dust storms on the Mars and how they actually cover the whole or half of the planet of the Mars. And there was a very recent dust storm in 2017 which actually engulfed almost half of the Mars. And there are many processes which is very different on the planet Mars compared to that on the Earth, which we have to understand, and that is why we are configuring a mission to Mars. Venus, on the other hand, is a very unique planet because the surface pressure of Venus is 90 bar. Surface pressure of the Earth is 1 bar. It's almost like 100 times more. So, the surface temperature is almost like 400 degrees centigrades. So, the surface of the Venus is very hostile, and that is why there have been no lander missions to Venus, because the temperature is so high, the pressure is so high. But there are many missions to Venus understanding its atmosphere, and on the in the atmosphere also the composition of the Venus is very similar to Mars. It is CO2 dominated, but it has sulfuric acid clouds around it at an altitude of almost like 40 to 50 kilometer altitudes, and they are almost completely covering the whole planet. And that is why this image which you are seeing is not the surface, it is actually clouds, and clouds are reflecting the sunlight. So, you are not able to see the surface in the visible, and that means you cannot use optical instrument to probe the surface of the Venus. You have to use other technologies, either use a microwave to look at the surface, or you fly an instrument with a 1 micron band window through which you can actually look at the surface. Otherwise, you cannot probe the surface. Not only that, when you go to an altitude of almost like 60 kilometers, the temperature and the pressure condition is very similar to that on the surface of the planet Earth. So, that means this is the region where you can actually go and fly something. And one of the ideas which is being floated is to have the ballooning around Venus at an altitude which is very conducive for its temperature and pressures. There is another big problem with the Venus is that because of this huge surface temperature and the pressure, when you go to an altitude of almost like 50 to 60 kilometers, these clouds which you are seeing over here, they complete its rotation around the planet in 4 days, whereas the planet itself is taking 243 days. So, that means these clouds are moving with very high velocities, or you can say there is a super rotation of the atmosphere. So, there are many processes by which the Venus is very, very different compared to that of Mars, though the dominant composition is same, it is carbon dioxide dominated. And that is why Venus is much more in what you call scientifically interesting to explore and to understand what is happening on this unique planet. Also, technologically if you look, Venus is much more difficult to reach because it is in the inner part inner orbit compared to that of Earth. That means you are going towards the sun when you are going to Venus, and it is not easy to go towards the sun because sun will pull the spacecraft. So, now you have to devise a mission with all the orbital mechanics calculation to see that you are able to reach Venus in a given amount of time. Otherwise, you cannot reach the Venus like what we have reached the Mars. And that is why we are also working out to see, when we devise this kind of mission trajectories, can we actually probe any other what you called object in the solar system like asteroids or comets, because it will take a long time for us to reach from Earth to Venus. So, this is the kind of scenario which we have in future to explore various planets in our solar system. We are also talking about a mission to asteroid and comets, either as a full-fledged mission or as a flyby missions when we go to Mars or to Venus, and also talking about a mission to Moon to explore the polar regions, because polar region of the Moon is much more challenging in terms of reaching or landing, but they are very exciting because rich amount of water is present there. And if you have to think about future human landings, you have to have some resources which you can utilize from the Moon itself, and one of them is water, because water is really required not only for the human beings, but also it can be used as a propellant or a fuel for launchings from the Moon itself. So, there is a lot of work going on about whether we can have a landing into the polar regions of the Moon in the future. So, with this let me summarize my talk and end very soon. We had the mission of the Chandrayaan-1 in 2008, we had the Mars orbiter mission in 2013, we had the Chandrayaan-2 mission in 2019, of which the orbiter is now working in its orbit. We are going to have the Aditya L1 mission to study the Sun next year, and then we are working on mission to Venus and Mars, which is likely to be in 2023 and beyond. And after that, we are also thinking about the outer part of solar system, but of course, this will be much more challenging. So, almost like 2025 or 26 to 30 time frame only, we will start thinking about going to the outer part of solar system, that is starting with the Jupiter or Saturn, because the travel time itself will be very large, number one, and also you have to gear up the technologies to survive this kind of harsh environment which you will face around the planet like Jupiter. So, thank you all for patiently listening.